Okay, this video is a continuation. It's part 3 of a series of videos on classification of linear second order PDEs. So in this video we are looking at examples where we are classifying each PDE as hyperbolic, parabolic or elliptic. Then in step 2 we are reducing each PDE to its canonical form. And then in step 3 we are finding a solution where it's possible. We say typically for parabolic or hyperbolic PDEs, then once you've got it in canonical form, a solution may be possible to find. Right, in the previous video, which is part 2, we have already worked on example A and example B. For this one, we're going to start with example number C. So in C, we're going to start by classifying the PDE as parabolic, hyperbolic, or elliptic. Right, so the first thing we're going to have to do is to write down our A and our B and our C. This time A is 1, B is 2, and C is 2. So the discriminant B squared minus 4AC is going to be 4 minus 8. So this is going to be negative 4, which is 0. This is telling us that the PDE is elliptic. All right. So if you watched our part 1 of this series, then you will know that we anticipate that the roots of the quadratic equation will be complex. So we are going to find the characteristic quadratic equation. Remember that one is given by A lambda squared minus B lambda plus C equals to 0. In the present case, it's going to be lambda squared minus 2 lambda plus 2 equal to 0. If we solve this using the quadratic formula, going to be 2 plus or minus square root of negative 4. We already found that in part A. So this is going to be 2 plus or minus 2i over 2. So it's 1 plus or minus I. So the two characteristic ODEs will be given by one of them is going to be dy dx equal to 1 plus I. So from this, if we integrate, we find that y minus x minus ix is c1. So that is going to be our xi canonical coordinate. And then the second one, dy dx 1 minus I. So when we integrate this one, we're going to find y minus x plus ix. So that's going to be eta. So in the case where these coordinates are complex, we introduce a coordinate system which is made out of the real and imaginary parts of xi and or eta, because as you can see, the xi and eta are just complex conjugates. So this is the real bit, just the same for this one, and that's your imaginary bit and negative for that one. So what we're going to do is we're going to let alpha by minus x, and beta bx. Even if you choose the minus x, it still will work out okay. Then we need to make sure that the Jacobian is non-zero. So alpha x is -1, alpha y is 1, beta x is 1, beta y is 0. So the Jacobian, which is alpha x, beta y minus alpha y, beta x, is going to be 0 minus 1. So it's non-zero. So we are good. So then after that, we just find the coordinates or the derivatives. So ux is going to be u alpha x plus u beta x. Alpha x is -1, beta x is 1. Okay, so that's going to be the ux. Then uxx is going to be u alpha minus, we're going to show you a quick way of deriving these ones towards the end of this video. So once you've got this one, then getting the second order derivatives you can be done pretty quickly, especially for the case where the derivatives of the variables are constants. Okay, so then uy is simply going to be u alpha, because beta does not depend on y here. Okay, so it's just going to be u alpha, and so uyy is going to be u alpha alpha. Okay, and then uxy is going to be negative u alpha plus u alpha beta. Okay, and so then we substitute into the ODE, substituting into, sorry, PDE. So remember the PDE is uxx plus 2uxy plus 2uyy plus ux equals to 0. So uxx is here, so that's going to be u alpha minus u alpha beta plus u beta, and then 2uxy is going to be given by that, and then 2uyy. Uyy is just u alpha, so that's going to be 2u alpha, and then ux is the negative u alpha plus u beta equal to 0. Then if you look for like terms here, so the u alpha terms, one here, minus 2 of them plus another one here, so they cancel. It shouldn't cancel out. Sorry. It's actually so one moment. Okay, so it's minus 2 of them here plus 2, so these two cancel out, but this one remains. So what's going to happen, these two cancel out, that one remains, so we still do have u alpha alpha. And then the alpha beta terms, we have minus 2 of them here, plus 2 of them here, so those ones cancel out. And then u beta is just that one there. So u beta, and then the first order derivative terms are just going to remain as they are. So this is going to be our canonical form for this, which corresponds to the form that was stated when we introduced the theory. In terms of the solution, this equation cannot be solved using the techniques that we have developed so far. Later we're going to see a method called separation of variables for second order linear PDEs that we can use to look for a solution of an equation of this type. Alright, so we're going to go to part D. In part D we have got y uxx plus y plus x uxy plus x uyy equal to 0. This PDE is defined away from the line y equal to x. So let's start with the classification. So A is equal to y, B is equal to x plus y, C is equal to x. So the discriminant, which is b squared minus 4ac, this is simply going to be x squared minus 2xy plus y squared. This is x minus y all squared. Since x is not equal to y for this PDE, this is always greater than 0. So that tells us that the PDE is hyperbolic. So notice that once we have got the type of the PDE, that directly tells us what type of canonical form we expect. Like this one, we expect that when we do the canonical or reduce it to canonical form, then only the uxi eta term is going to remain in the second order derivative terms. All the other two second order derivative terms, we expect them to cancel out if everything has been done correctly. Right, the characteristic quadratic equation is going to be y. So this is going to be y lambda squared minus x plus y lambda plus x. Using the quadratic formula, this is going to work out to x plus y plus or minus the square root of x minus y all squared divided by 2y. So this is just going to be x minus y. If we add these, the x's are going to add and the y's are going to cancel out. If we subtract, the y's are going to add and the x's are going to cancel out. So one of the roots is going to be 1 and the other one is going to be x over y. So the characteristic ODEs from these two will be, first we're going to have dx dy is x over y. So this is going to give us y dx, sorry, y dy minus x dx equal to 0. In integrating that, it's going to give us y squared over 2 minus x squared over 2 is equal to some constant c1 asterisk. Multiply everything by 2, then just to simplify things, then our xi can be written as x squared minus y squared equal to c1. Then the other characteristic quadratic is dy dx is equals to 1. So from this one, if we integrate, we find that y minus x is the other canonical coordinate. Then we check for the Jacobian again. So xi x is minus 2x, xi y is 2y, eta x is minus 1, eta y is 1. So the Jacobian is going to be minus 2x times 1 minus minus 1 times 2y. It's going to be negative 2 into x minus y. But this equation is defined away from x equals to y. So this is always non-zero. So we're fine. Then we can now start to work out the derivative transformations. So ux is going to be uxi times xi x. It's going to be minus 2x uxi. And then the other one is going to be minus 1 u eta. Then the xx derivative, I'm going to do it quickly. Then, like I said, we were going to give you a principle of how to work these out a bit quicker once we've got the first order derivative. So it's going to be 4x squared plus 4x uxi plus u eta eta, and then derivative of this with respect to x is just going to be minus 2. So there's going to be that first order derivative term. Then uy is going to be 2y uxi plus u eta. This is because eta y is 2y and xi y is 2y and eta y is 1. Okay, so uyy is going to be 4y squared u xi plus 4y u xi eta plus u eta eta plus 2u xi. Then uxy, so that one is going to be negative 4xy uxi eta minus 2 into x plus y uxi. Sorry, the first one is xi. So xi here, xi eta here, and the last one is going to be minus u eta eta. Then we're going to substitute into the PDE. So the PDE becomes, so we're going to have y into 4x squared u xi plus 4x u xi eta plus u eta minus 2 u xi plus x plus y into negative 4xy u xi minus 2x plus y u xi eta minus u eta plus x into 4y squared u xi, this is the uyy term, plus 4y u xi eta plus 2u xi okay, and then equal to 0. So that's the last term there. Now let's check for the like terms and see what happens to them. So let's start with the xi term. So we've got 4x squared y xi. There's going to be minus 4x squared y from here, the first term. Then 4xy squared is going to be minus 4xy squared. So these terms are going to cancel out. Then the xi eta terms, there is 4x here minus 2x. So that's going to leave us with 2x. There's 4y here. This is all multiplied. Okay, maybe let's just do these step by step so that we are all happy. So there is 4xy from here, okay, minus 2x plus y squared from here, plus 4xy from there. Okay, this is all times u xi eta. Okay, then the eta terms, there is y eta minus y eta from here, and then there is plus x eta minus x eta. So these two 3 cancel out. Then the first derivative terms, we have got plus 2x from here minus 2y from there u xi. Okay, now so let's work out this first term here. So this first term is going to be 8xy minus 4x squared minus, it's actually 2x squared, then minus 4xy and minus 2y squared. Okay, so let's just work this out first. So if we factor out 2, okay, a negative 2, this is going to be x squared. Then 8 minus 4 is 4. Factor out 2, it's going to be 2, so it's going to be negative 2xy and then this is going to be y squared. So basically what's happening here, this is now x minus y all squared. So what's happening here is this PDE is negative 2x minus y all squared uxi eta plus 2x minus y uxi equal to 0. Since x minus y is non-zero, we can divide everything by negative 2x minus y. So we're going to have x minus y uxi eta plus uxi equal to 0. Now, typically our canonical form, we need it in terms of the canonical variables. So we've got to ask ourselves the question, what is x minus y? Sorry, there is a just one moment. This has got to be negative here. Okay, so we've got to ask ourselves the question, what is x minus y in terms of xi and eta? And we're going to remember that eta is y minus x here. So that means this thing we can write as negative eta uxi eta minus uxi equal to 0. So we can simply just multiply everything by negative 1, and so that is our canonical form. Then for part 3, we're going to integrate this. Since we have got a derivative of xi in both of them, and this does not depend on xi, then we can integrate partially with respect to xi, and so this is going to give us a function of eta. Then you're going to notice that this is an exact derivative. So if you differentiate u eta, you get that using the product rule. So that means u times eta integral of h, okay, let's just call it integral of h with respect to eta, and then there's going to be a function of xi. Then so u is going to be integral of h divided by, this divide is like this, integrate first, divided by eta plus f of xi divided by eta. But this first one we can simply just call it g of eta because it's entirely a function of eta. So that is going to be the general solution of our PDE. Now, in terms of the original variables, then we can write this as u of xy. It is going to be equal to g of y minus x plus f of y squared minus x squared, all divided by y minus x. Okay, so that's going to be our general solution. Now, what I'm going to do now is we're just going to take a few minutes to give you an operational way of getting through your derivatives quickly. So what we are going to do is going to help you sort of get some principle of how to get these second order derivatives given the first order derivative. So the first order derivative, you definitely have to know how to work them out. Then once they are there, then we want to give you, that's going to help you to get the second order derivative quickly. In order to do that, we're going to appeal to the chain rule situation here. So we have got u, which is a function of x and y. Then we are transforming it to u, which is now a function of xi and eta. Xi is a function of x and y. Eta is a function of x and y. Now, if we start with derivative of u with respect to x, okay, so now we want to differentiate this with respect to x, but it depends on x through xi and eta. So that's why we have got to do partial u, partial xi, then partial xi, partial x, plus partial u, partial eta times partial eta, partial x. Now what I'm going to do is I'm going to write this as xi x. This one I'm going to keep like this. Same here, eta x, partial u, partial eta. Now, before we do the second order derivative, it is important to note that the xi and eta are functions of x and y, while the u's are functions of xi and eta. Okay, so xi and eta here, x and y here. So as we go to do another derivative, which will be the second with respect to x here, so we're doing partial x of partial u of x. So this is what I'm going to do first. Just going to write this exactly as it is. Okay, eta x, partial eta. So when it comes to these two, they are functions of x and y, so we can differentiate them straight away with respect to x. We don't need the chain rule for those ones. Okay, so what I'm going to do is so that means here we're going to use the product rule. We're going to start with this term, differentiate it straight with respect to x, then we keep this fixed and differentiate this one with respect to, because it depends on xi and eta, then for that one we need to use the chain rule. So for this one, it's just going to be xi xx, which is the second order derivative of xi with respect to x. Keep this one fixed. Okay, so by the product rule. Then now we're going to keep this one fixed and differentiate this one. Now, since this one is a function of xi and eta, so we're going to follow the same procedure that we did here, because here we're differentiating u of xi and eta. So, but this is already a function derivative of xi. So if we differentiate first with respect to xi, this is now going to be the second order derivative with respect to xi. Then we do the derivative with respect to eta and multiply by eta x. Okay, so we're keeping this fixed, just differentiating this with respect to x, but going through xi and eta. Then we're going to do the same thing for this term. So the first one is going to be eta xx, keep this fixed, then we keep eta x outside. Okay, so this one is already derivative of eta, so if we differentiate it with respect to xi, then we're going to have xi x outside here, so xi x. Then in the second case, we differentiate it with respect to eta, which means we're going to have second order derivative with respect to eta. And then if we remove the brackets and collect terms, so we're going to start with the second order derivative terms first. So this one is going to give us xi x squared, second order derivative of u with respect to xi. Then these two terms are like terms. Both of them have got xi x eta x, xi x eta x. So there's two of those. So we're going to have 2 xi x eta x, second order derivative with respect to xi. And then the last order 2 derivative is going to be this one with respect to eta squared. And then they're going to be these first order derivative terms here, depending on whether the second order derivatives of xi and eta with respect to x, whether those ones are non-zero or not. Now, my focus is on the second order derivative terms. So what I want you to notice, okay, I think what I'm going to do, let's just erase this just for instructional purposes, and then I'm going to write the first order derivative here. So ux, this is now ux is xi x uxi plus eta x u eta. Now what I want you to notice is that with the second order derivative term with respect to xi is multiplied by the square of this term. Same thing, second order derivative with respect to eta multiplied by the square of this term. And then the middle term is 2 times this times this. Okay, one. What do you notice? Well, you notice that the coefficients are binomial-like, you know. So if you were to do this, okay, then just in terms of the coefficients, the first term coefficient is going to be xi x squared, last term coefficient is going to be eta x squared, middle term coefficient is going to be 2 times this times that, and that's always going to be the case for the second order derivative terms. So once you've got this one, then we can get the second order derivative terms straight away by using the fact that the second order derivative coefficients are binomial like. What does this mean? This means if, for instance, ux is 2uxi minus u eta, and uy is 3uxi plus u eta, then you and mind you, if these coefficients are constants, because it means, so here it means this one is xi x and this one is xi y, and 1 is eta y, -1 is eta x. So naturally xi xx is going to be 0 and eta xx is going to be 0. So that means these terms are not going to be there. We're just going to have the higher order terms. So in this case, so uxx, so the coefficient of this is going to be the square of that one. Okay. Then the coefficient of the middle term is going to be this one times 2, which is going to be -4. And then the coefficient of the last one is the square of this one. So it's going to be like that. And there you are. I've got uxx. Uyy is going to be 9, which is the square of 3. Second term is going to be 3 times 1 times 2. So 6u xi eta. And then the last term is going to be u eta eta. Okay. Then the mixed derivative term again we can find. So this and this gives us u xi xi. This times this gives us 6. Then the mixed derivative term, you have got this and this. 2 times 1 is 2. And this and this, 3 times -1 is -3. So that one is going to be -1 u xi eta. And then this times this is -1 times 1. So it's going to be -1 u eta eta. All right. So that's basically how they work out. Just going to scroll back here. So let's look at these two, for instance. Okay. So you can see that the coefficient there is -2x. -2x squared is 4x squared. Then this one is -1, so that's why that's +1, square of that. And then -2x times -1 is 2x, times 2 is 4x, so that's why that one. Okay, but because the second order derivative, so here when you do this, you're going to have to use the product rule. So when you differentiate this with respect to x, then that's when you get this one. So that's why you've got that first order derivative one. So it's because here xxx is the -2, so that's why you get that one. Okay, otherwise if you go to the mixed derivative term, for instance, then xi is going to be times -2x times 2y, which is -4xy. Then you do this -2x times 1, you do 2y times -1, and then you get the coefficient for the mixed derivative term. And then here it's got -1 times 1, so that's why that one is -1. Okay, so that's how you can well, work out the second order derivative terms a bit more efficiently. Right, so hopefully this example or this video has been helpful. What we are going to recommend you do is to have a go at E and F, and then our solution is going to be presented in now part 4 of this series of videos. So if you have a go at E and F, and then if you check part 4 these videos, then you're going to find our solution. Thank you. Hopefully this has been really of help. Please do subscribe so that you can get notified whenever we post new material.